Okay, so we will continue. I received some tasks, certain solution of the problem which I gave from some of them. So, but today is last day, as you remember. Okay, we will continue, and we finished on the we consider it's Einstein equation for with a lambda term. So, and what we discovered that the cosmological constant, so I will remind here, this is lambda, we call the cosmological constant. It looks like that this constant can correspond to such a kind of component of such a kind of matter of, we will say, about energy, because we can see that there is this correspondence between lambda and epsilon. This such a form of matter that the pressure of this matter has a negative value. Also, if you remember, we used in Einstein equations the positive value of cosmological constant. If we will put a negative value, so in any case we will obtain finally like this. I also would like to say that there is a doesn't matter. We speak about language. It's not useful now. Okay, so now we will start to work with. I want to use some time to speak about static Einstein model, since we discovered that Einstein exactly included lambda constant, lambda term to find the solution for the static universe and how it is working. So really, if we will, let's write. Just a second. I need to find my phone. Where is my phone? Okay. Okay. So static model of universe. So which was an idea? The idea is such a way that if we will look on the Friedmann-Lemaitre equation for the acceleration, let's write it. So A to point divide on A. We obtained it before, so I just remind where it is. This one. So sorry. Minus 4pg divide c 3c square epsilon plus 3p, and so we want to keep lambda term, so it will be here plus lambda c square divide on 3. After this, we can ask questions. So look, and this was an idea of Einstein to consider the universe, which consists of the non-relativistic matter, so just a star like this. Stars are very hit, and you need to understand that this time we even was not sure that there are different galaxies. So it was a discussion this time a little bit later about what is this nebula on the sky. So let's consider that we have some non-relativistic matter, And it means that equation of state correspond to the equation of state of dust. So we consider situations that we don't have collisions. In this case, we have such a way that it's disappeared. And and we can look on this equation. By the way, it's for example, if we will come back to just to remind that we found the Einstein equation go step by step from classical mechanics. So I will remind that the equation for gravitational field, this is Poisson equation. I don't remember we used for the potential big field, small field, don't remember. Oh, okay. Where phi, this is graph potential. Okay. This is Laplacian on the left of the graph potential, so operator Laplacian. And we understand that on the right side we need to put 4 pi g rho. Okay, this is Poisson equation. If now we understand that we also have some constant, it should be very small, but this constant exists. In this case, if we will start or we will connect this with the classical mechanics, we need to put here plus lambda c square. So and the point that you can see that in this case the Poisson equation really changed a little bit with some adding of some constant. So, and it's understandable that if you want that everything will correspond to the classical mechanics, we understand that this constant should be very small. We will speak later about this. For now, we are working just with the, with the terms. Okay. So, what we want is from the point of static universe. It was really considered that the universe should be static. It's even come to us from ancient time when people believed, starting from Aristotle and even earlier, that everything which is related to the sky should be much more, how call it, ideal, and from the point even, and maybe this also was something, of course we understand that we have a motion like this, but to consider that the universe can evolve as a whole was really something strange for this time. So, and much more comfortable was to suspect, to suggest that it could be static. Providing, because when we speak about static, it means we speak about evolution of the space, but not the object inside of the space. Of course, they are moving like this. So, and the idea was to include this lambda constant, lambda term, and after this to look, can we really obtain the static universe? It means that the velocity of scale factor should be 0. Okay. So in this case, yeah, we also need to come back to another Friedman equation for acceleration, for velocity, this one. Okay. So, and if now on the left part, I will use here my pencil. On the left side, we have a 0, since we decide to put a point equals 0. So on the right side, we will have okay, let's see. Okay, 8p g divide on 3, and I will put just a density, so I will already will put RC square, and C square will disappear, the speed of light disappear, minus we also have a summand which is related to the curvature of the space, so k c square divide divide on a square r0 square, and plus lambda c square divide on 3. So again, since we decide that, since this universe is static, it means A equal constant, and it means that we can rise here for and constant, and we can put equal 1. So it means equal a0. A0, this is correspond to present time. We already decided to use a equals 0, and this just, it's much more convenient to look how evolve the space in the universe corresponding to present time. So in this case, I can just kill here A, and this equals 0 from the left. Okay, and this part I can a little bit change. So now I need to understand how I can change it. Okay. 8p g3 multiply on rho. And I can change it using already obtained expression. Kc square, I need to find it for the present time. Okay. Let me think. Okay, I can use this one. Look, from this. If you look on this, is also Friedmann-Lemaitre equation, but since we consider for the present time, we can write that the Hubble constant on the left side will be equal 0, and we can write that 8pg3c square epsilon equal kc square divide on r0 square. I don't remember the where is it should be okay, I don't remember now. Maybe I will remind this a little bit later. But the point that the summand for for this case is a point, so equal a equal equal 0, a equal constant. It must became 4p I don't remember where I lost 1.5, but I will think later and will tell in the next lecture. Multiply on row. So this is question and okay, I will not spend now time to think for a long time about this. So yes, maybe somebody understand already. Oh, okay. So what is the trick? The trick is such a way that finally we will have finally that in this case we have 4p g row equal okay, understand. Okay. Okay, but I understand why there is, so we need to do some additional procedure. Okay, I will to give you the proof a little bit later. I just want to show to say you that final equation for the static universe should can have this the following view. So, and the idea is such a way is that the static Einstein universe can exist only for the case when k equal +1. So, and you can even to find the just a second, I want to understand. Oh, okay, 0 equal to p g c square epsilon c square r square plus lambda c square divided by 3. From this we obtain z minus zkc minus kc square r square plus lambda blah 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 equal plus minus equal epsilon. So but why 4? Sorry, I it's really sometimes some point I don't remember, so I don't understand why finally we lost 1.5. It should be everything right, but it's, you know, sometimes we can lost in 3 trees. So in any case, later I will discover what is the problem, and it should be something very simple. What is the problem? And this is just, you know, for historical point, but also it represents that I would like to show you that, and we will see also later when we will consider the stage of the universe, of the evolution of the universe. What is the problem? The problem and why Einstein was not happy with his introduction of this lambda term, cosmological constant. Because from one point, it's really made the theory not beautiful because, as already said, you involve some constant, additional constant, which should be fundamental. The second point that this universe is not a static. So, of course, you applies conditions that this velocity of scale factor should be 0. And okay, it's you impose it, so and you and it should be like a static. But the problem that this equilibrium is not stable. This is unstable equilibrium. Unstable equilibrium. Why? Because if you have in some moment of time the balance between forces which are related with a cosmological constant and these repulsive forces from another side, from one side, from another side, you have matter and you have gravity, and you have attraction forces. But if you if you will take some volume, so in this volume you Wolf volume, okay, so you this volume will evolve like this, and if you will estimate the energy density of the matter, and we call energy density of the matter like epsilon m, so it will be proportional to 1 divided on a cube. Why a cube? Because it's the density decreasing corresponding to increasing of the volume. So it will be like this. But we discovered that density, energy density for the cosmological constant is a constant. And it means that if you sooner or later we will not have an equilibrium between we can have an equilibrium in some moment of time, but if something will be changed or in some special condition, so these forces, this force, I mean the force which are related with a cosmological constant, which we call now dark energy, so it will be much bigger than this one. So, and finally, cosmological constant will win. And sooner or later, the universe will expand corresponding to this equation of state. This is the point. So, and after this, Einstein says that this was a big mistake in his life, and you will see that now we will use this solution and this cosmological term to explain the recent acceleration of the space in the universe. But before to do it and to see it clearly, so with this, we will finish with the static model of Einstein. And just will put for me this equation here. I remember this. It's just something should be very simple. Now we will speak about how called to formulate it. Okay, one component models of universe. What it means, one component? It means that we will now to fill the space of the universe with such a kind of matter, and we will see how it will evolve due to this. So, after this, as soon as this will help us to understand the next step when we will consider the multi-component of universe. We already will understand how in principle universe can evolve from these models. To do this, we will use our equation which we obtained okay, from the first law of thermodynamics, this one. Okay, so which is the relation between energy density and the pressure. And I will write epsilon point plus 3 A point A P plus epsilon equals 0. And I want to consider it for the general equation of state, like this, where W equal constant. And the constant tell us which exactly matter we consider. So, and I can, to find the solution of this, so it means that I can write here some point plus 3, like this. Epsilon and 1 plus W, right? Equals 0. So, or I can write that it's d epsilon divided on epsilon minus equal minus 3, 1 plus W, dA divided on A, right? So, and we can simply integrate it and we can have logarithm, natural logarithm epsilon divided on epsilon 0, where we integrate such ways that the constant of integration will correspond to the present time. So now I will explain logarithm and A divided on A0. Power will be 3W plus 1. So it means that A0, in principle, it is not important to write F0 because we can put it unity. So it means that we would like, again, this is present time. So it means that we would like to understand the behavior of the space relative to the present time. And since we know that the radius between, distance between two objects changes A on T multiplied on R0. So it's exactly correspond when A equal A0 correspond to the present time. So present time, it means that R, it means that we need to put just 1 multiplied on R0, so this is R0. So this corresponds to the distance between objects for the present time. And correspondingly, energy density, epsilon 0, this is epsilon for T0 on T0. Just a second, Thomas. So, okay, so we can write now for the epsilon that the energy density equal epsilon 0. I think there is a mistake here. I think I need to put here a minus, right? Yes. It's obviously. Are you here?
Yes, we are here.
Yeah. Yeah, please check what I write, because if I can make a mistake, and after this it will be painful to find. So I agree that it should be here minus.
According to previous expressions, yes, here must be minus.
Okay, so okay, now I will write opposite, something like minus. Doesn't matter. Okay, so this is equation. We even can right, for us it will be more convenient. Epsilon proportional a minus 3 double v plus 1. So this is this one, this way, or this one. It's important to understand, it's very convenient that we can see immediately that how the density, the energy density can evolve due to corresponding matter which we will put in the universe. So, and we will see it. So if we, for example, we will have double V equals 0, we have that epsilon proportional A minus 3. And it's understandable again why we already discussed this, because when we have one volume and after this it's evolved like this volume, so it's understandable that it will be 1 divided on a scale in the cube. So everything understandable when we speak about non-relativistic matter. So this is for non-relativistic matter. If we have situation for the relativistic 1 divided on 3, so in this case, in relativistic, it means photons, okay, electromagnetic emission. So in this case, we can see that plus 1 will be 4 divided on 3 and 3, 4. Okay, so we see that energy density proportional A minus 4. It's also understandable why, because what is the dimension of the density energy? So it's energy divided on L cube. And if we will write, okay, H nu, or it will be proportional, since we can express frequency through the wavelengths, so it will be exactly, so everything understandable. This is for, okay, for relativistic matter. It's a photon, it's photons, and also can be neutrinos. We have that there is a problem for when we put double V equal 1 minus minus 1, because in this case we will have no, we don't have any, so we have a double 1 minus 1 plus 1 equals 0, and A in the 0 it looks like some constant, so everything in principle, let's put it like constant. Okay, So this is what we have. And in principle, when we speak about one component of the universe, we speak about three cases. When the universe consists of the non-relativistic matter, relativistic matter, and only cosmological constant, or some kind of the matter which has negative pressure. Now let's see how scale factor will evolve due to its corresponding to the one of the state equation. So for this we will use Friedman equation. So what about A as a function on T? Question. How evolve the scale factor? To do this, we will use square Friedman-Lemaitre equation here, this one. And okay, Friedman-Lemaitre equation, as we now already understand, we can write it without this part, but just considering that this is like this. So we just, instead of this, we put here epsilon lambda. Okay, you just can make some remarks in your conspect, which we discovered before. So, okay, so let's see what we will have. And I want to consider just to more simple case, or you know, one case when the signature of the curvature equals 0, because it's more simple. When k is not equal 0, we can speak about this, but for us, in principle, much more interesting this case, because universe exactly correspond to the case of the flat space. So, and just to feel the behavior of the scalar factor, it's enough to consider and to see what we will have from Friedman equation. So multiply an epsilon. So we killed the summand with the curvature of the space, and lambda, if we want to put it, it will be here. Okay. So we already know that epsilon equal epsilon 0. Multiply on, and I don't want to keep this a0, so let's consider that this is equal 0 for now, and as we agreed, minus 3 double v plus 1. So if we will put it on the right side, we will obtain that a point square equal 8pg3c square, and a, and instead of epsilon, we need to put epsilon 0, and also it will be a square multiply on a minus 3 double v minus 3. Okay, together it will be a minus 3 double v minus 1. So you can rewrite it, but I do like this. Here, multiply on a minus 1 plus 3 double v. So if we can see that we can integrate this equation. Again, you can rewrite. I will correct here. I will kill here this one, and I will write here 1.5, and here divide on 2. So, and after this I can write that dA multiply on A 1 plus 3W divide on 2 equal, let's call this such a constant. For example, let's all of this call A. So it will be A on dt, because again a point equal dA divide on dt. So, and if we will integrate, so we need to integrate from I want to integrate from beginning, this is constant, from beginning, from the time when we consider the cosmological singularity, when universe was born, creation time, okay, and to the in the principle I can find the I can integrate from 0 to T0 and from 0 to A0 to obtain the constant. From this I can find the relation between T0 and A0. So it's important such a kind of things, because it will be important to calculate right age of the universe. So if we will do it, we will have that the relation between T0. So from the right side we will have T0. I want to find the relation between. So after integration we will have 1 plus double V multiply on A. And now I want to just, because you will see now I will make some tricks. So now I want to solve this equation for a general case, for the another size, for the another part of the evolution of the universe, starting from A0, from the present time, and to some A in any time. So again, equal A, and here I will put T0 on T dt. So if I will integrate it, so what I will have, you can, I don't want to spend, so I know the answer, we can do it, of course. So what we will have maybe this will be something like this, because, okay, let's do it now. So we will have 2 divide 1 plus 3 double V. We will have, and now I will put this constant, the integration constant, such a way that it should be in denominator. It's convenient will be for me. So here I will have after integration. So what I will have 1 plus 3 double divide on 2 plus 2 divide on 2. So I will have 3 1 plus double V divide on 2. Okay, and here I have A multiply on on t. Mhm. Divide on t0. So finally we will have that a yes, like this. A we have dun, 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 dun. Give me time to think. Mhm. No, I think it's better to put here. Sorry. I think it's better to put here from 0. It doesn't matter from which point we want to integrate it. Okay. So I will put here 0. In this case, oops, so I will kill here I0 and I will kill here t. So if I will write 3, 1 plus w divide on 2, so equal, and here I will have 1 2 divide 1 plus 3 w multiply. I want to write this square root 8pg3c square epsilon 0. Of course, here should be, we made a mistake because, of course, here should be the same what is in the denominator. Okay, so it's a just mistake. So, and we can put it, instead to put in front, I can put it here. Oops. 4. Here also should be. No, today I made a mistake. I'm sorry. I'm not not in a good shape today. Sorry. So it was 2 divide on 3, 1 plus w. Okay. So and instead of this, I will put here 4 divide on 9. Just want to reach the trick which we need to obtain finally. And multiply on t. Okay. So finally, what we have? We have a equal incredible. Today I'm not in good shape, so I need to And you don't help me, so where I made a mistake. Look, it should be here, so now I will write everything right way. Okay, so 2 divide 3, 1 plus double V, A3. When I try to be much faster, it's really became worse. Multiplying 2. Okay, after this go in this side. So we have A3, 1 plus double V, divide on 2 equal 1 plus double V. And here we will have 8, 9 divide on 4, PG, 3C squared, epsilon 0. Multiplying T. So now it's correct. So here we have a 2, here we have a 3. So together it will be 6. And this is exactly correspond 1 divide on T0, which we found here. So this is trick to, it should be like this. So finally, let's jump to the final expression. What for us much more important, this is exactly this power law which we obtained here. So we have set A behavior like doesn't matter, 0 we put unity, T divide on T0, 2 divide on 3, 1 plus double V. So this is for us much more important. We can put here a 0 if you want, or just consider this as unity. I just wanted to be much more consequent to prove that the Newton principle, to check that this summand has a dimension which equal 1 divided on time. And if we will ask what exactly this time, we in principle can recognize that here there is a epsilon 0, so it's related to the present time, to the T0. So at this point, I just wanted to show that this is, and in principle, this T0 and this expression, you can see that it's related to the present time. It means the time in which we calculate from the birth of the universe. So when when we consider the evolution of the universe, we consider this is 0, the time, okay, and this is T0. This is present. This is birthday of the universe. So 0, and this is past. This is future. And if we will put here the scale factor, oh, sorry, stupid. The time increasing, yes, but the time increasing, but the scale factor increasing too. So this is also, so the scale factor was 0 when it's birthday, in the lifetime work of Friedman cosmology, and after this it's increasing, and we need to understand it. So will be all time increasing or not? So okay, what we can see, and this is exactly we obtain now the dependence between the scale factor and time. So, and as soon as we have epsilon as a function of scale factor, and we have a scale factor as a function of t, so this is idea that in principle we can understand the dynamics. Okay, so for example, let's see on the let's write age of universe. And I will impose Okay, age of the universe. It's understandable for one component model. For one component. I just want to show you some paradox which we will have if we will consider the universe, which consists of only non-relativistic matter. Non-relativistic, it means stars, planets, galaxy, and like this. So let's do this trick. So to this calculation. So if we will consider, let's write here T0. Okay, 1 divide 1 plus double V, C squared divide on 6P G epsilon 0, 1 divide on half, divide on 2. So if we will Hubble constant, and as you remember, we discussed that in the beginning, in the first lecture, that since Hubble constant has a dimension of 1 divide on T0, in principle, the Hubble constant allow us to estimate of the age of the universe. But let's look more careful. So let's consider that. So what is H0? H0, this is a point divide on A on the moment of time t equal T0. And let's calculate. Now we have A from here. So A point, and we need to find the derivative from this expression. So now I will try to be much more careful. 2 divide on 3. I know why I made a mistake before, because my colleagues invited me for the lunch now. Beautiful place, and I needed to cancel this invitation now. So maybe my brain became a little bit upset. Okay, so like this, and and to find the derivative of this part with a t, I will write like this: t divide on T0, 2 divide 3, 1 plus double V, and due to the derivative, I need to put in the power law -1, but I will write it like this. Okay, so this I can see why I put like this, because this is exactly scale factor. So, and finally I have that a point equal 2 divide 3, 1 plus double V, 8 divide on T. From this I can immediately see that a point divide on A equal 2 divide 3, 1 plus double V, 1 divide on T. So, and if I want to write H0, a point divide on A, T equal T0, it means 2 divide on 3, 1 plus double V, 1 divide, and I need to put here T0. So we found now the expression, much more precise expression for the age of the universe. T0 equal 2 divide 3, 1 plus double V, on 1 divided on h0. So this is expression for the age of universe for one component models. What it means? It means that we can, for example, and what we can see that if we I want to look, okay, I can see a non-baryonic matter. I mean, I can see a lot of stars, galaxy, gas, so, and for this non-relativistic matter, for the normal matter, I know that W equal 0. So non-relativistic matter, which we understand that is everything what, of course, everything what we can see, it's due to also emission which we receive. But in principle, I can tell in advance that for now, the energy density of the radiation is really small with comparison to the non-relativistic matter. So for this case, I have T0 equal 2 divided on 3, 1 divided on H0. You can, so if you will calculate this the age of the universe, and it's simple to do because we can take, for example, H0 is 70 kilometers per second, a megaparsec. So, and you know, you need only to Mama mia, it's already time. You need only to write it in the seconds, you know. So if you put it here with the right dimension, you will see in per second that T0, which you will obtain for this, it will be approximately 9 billion. 10 on the 9 years. 9 billion years. Which is not right. So because there is a problem in this case, you already can see that if we will put only matter which we know, non-relativistic matter, the age of the universe is less than the age of some objects in the universe. What exactly objects? For example, we know we have such independent method which can tell us about the low limit for the age of the universe. For example, this is due to the radioactive elements, and for example, we understand that the age of the universe can be less than the age of the Earth, because it's stupid, or the age of the stars. And one of the possibility to find and the low limit for the age of the universe, it's like approximately, it's should be even larger than 10 billion years. Why? Because we can see such a kind of object which we call white dwarfs. This is the end of the evolution of the stars, and we know very well the function how this relativistic object, these white dwarfs, evolve. We know very well this function of the luminosity due to the time of this object. And but it was discovered that and it's understandable that since this white dwarfs, these stars which consist of degenerate electronic gas, and they are in equilibrium due to this. And when we, if you will look on this distribution of these stars, you will see that starting from some low, so from some value of luminosity, the number of these white dwarfs really drop to some few numbers. So it's really there are a few, not a lot of such a kind of objects. And one of the explanations that the age of the universe was not enough to have these stars with such a kind of that they became so cold that they became so cold that luminosity is so low. So this is one of the also limit on the age of the universe. So with this I want to show that even if we will take, because now we know that the age of the universe around 13.5 like this billion years. So we lost, we don't have, we need to add something like 4 billion years. This is already presentation that we can't consider the universe only with presence of one matter as relativistic matter. We need to add something else. Soon we will see that if we will take into account the other components, including dark energy, the age of the universe will be away from the point that this is not known. So I also I have 10 minutes. So what I also would like to say that from these models already we can understand that, and to say in advance also we can see from, so if we will summarize for now, so we can see that for double V equals 0. Sometimes this model called the universe of Einstein de Sitter. So in sense that it's filled with a non-relativistic matter. There is another model, model de Sitter, which is filled only of cosmological constant. So, but Einstein de Sitter. For this case, we have A, which is proportional, and we will look on this 2 divide on T to divide on 3. So what we can see is that universe will expand infinitely. Of course, we consider the case only k equals 0. The universe will expand infinitely. The density, so we can equal A minus 3, proportional, okay? Proportional T minus 2. For the double V equal 1 divide on 3, this is a relativistic matter. So again, k equals 0. We have, for this case, that what we have is, okay, okay, yes, epsilon proportional A minus 3, we already spoke about this, minus 4. And if we will put scale factor, corresponding to what we obtained, it will be t 1 divided on 2. So in future we will call, and this is relativistic matter. So what we also can see, for example, we even can feel already some possible evolution of the universe. Since we in advance understand, and let's call it, for example, for a relativistic case, I will put index here, radiation, and here I will put, for now, dust, for now. After this we will maybe recall. I can see that if you will write on one picture, the scale factor and energy density, we can see that for one case, W equals 0, it will be, for example, like this, and this corresponds to epsilon dust, okay? And for another case, I exaggerate, of course, like this, because it's understandable that epsilon radiation due to scale factor a minus 3 and this a minus 4. So, and if a if a tend to infinity, in this case, W equal 1 divided by 3. In this case, of course, put like this, just you know, will decrease more quickly than another equation of state. And if we understand that in the universe we need to have anyway the total energy density as a sum of the radiation and the matter which we have. So, and we understand that in this case that we can divide the evolution of the universe on two parts. So, which correspond to some time. Let's put it for now, the star. And in this part of the, this is 0, okay, it's the birthday of the universe. For this part, epsilon radiation more than epsilon dust. And for this part, epsilon radiation much less than E dust, epsilon dust. So, and we already can see that if we, for example, consider universe consists of these two components, we can see that we can divide the evolution on two stages. The first one, and it's called radiation dominated, when epsilon radiation is larger than ED,
Yeah, but maybe on this graph we need to put near W equal 1 divided by 3 epsilon dust, because I think that it corresponds to this case.
Say again, epsilon radiation here, you mean?
Here must be epsilon dust or not?
No, epsilon dust. I made, sorry, here mistake. Here should be dust, and here should be radiation, of course. Corresponds. So I'm sorry. Sorry. Yes. Thank you. it should be radiation. So, thank you. And the second one, this is so the where we can say this is stage of non-relativistic matter. When epsilon dust more than epsilon radiation. So this we already can understand that the history of the universe, in the sense that some times ago, and the point when it was, we will find it in the tomorrow, because we will have a lecture tomorrow. So before it was sometimes before it was really it was a stage of radiation dominated stage, and it's understandable because, and we will see it because the temperature of the universe is increasing when we go to the past. So, and otherwise the universe became like colder when we go in the future. So the future, you know, it's not so beautiful from the point of mean temperature and energy. So this is what I want to say for today. Unfortunately, time is passed, so I will make a screenshot. If you have any question, please ask. Because now I need to go in another Zoom where they need to, university need to explain us how we need to use Moodle to evaluate your knowledge. Okay. So, do you have some questions? No? Okay, in this case, see you tomorrow. Tomorrow we have a lecture, as you know. And tomorrow I hope tomorrow we will speak about cosmological horizon, how it's evolved for different models. It will be, I hope, quickly. And we need very quickly to go already to multi-component of the model of the universe. And of course, we will look what's happened when we put only cosmological constant. So, okay, see you tomorrow, and good day for you.